So for uniform circular motion involving friction for an object that is a car usually, or some such thing, moving in a circular curve. If we're moving in uniform circular motion, that means we know the net force has to be directed inward, and is the centripetal force. And if we look at this car from back here, so if we view it from the back as it goes around the curve, that'll be our car. It has its weight, obviously. It's got normal force. Those two are going to be equal because this is a non-banked curve. This is a level curve. We'll get to banked ones later. What is moving the car in a circle and causing it to change directions, because you've turned your wheel, is friction. And that happens to be static friction. And I'll give you a quick explanation as to why. You imagine your wheel rolling as you move down the road with some velocity v. That tangential velocity, that speed with which your car, so the center of this wheel, is moving down the road with v. But at any given moment, any point on the car, on the wheel, on the outside of the wheel, is also moving with v. The same velocity. Which means that at the top, this point, at this instant, is not only moving because it's rotating, has a tangential velocity of v, it's also on a car that is moving. So it has the same velocity that way. So its actual velocity at that instant is 2v if it's on the top. But what happens at the bottom when it's in contact with the road? Well, because it's on a car moving down the road, that point does have a velocity this way of v. But because it's rotating, its tangential velocity at that moment is also v, but in the other direction. So its actual velocity at that point is 0. Strangely enough, at the instant it hits the ground, its velocity is 0. That means static friction, which is why it's not good to lock up your wheels, because then you go to kinetic friction, which we know is generally less. So, one of the interesting parts about wheels and spinning and so forth is that they use static friction, which is why anti-lock brakes are so important these days. When I was growing up, we didn't have them. Yeah, so count yourself lucky. All right, so knowing this is the case, that means that your net force is your centripetal force, and it has to be friction. Okay, so the centripetal force comes down to the force of static friction. Now, in a lot of these problems, they're not going to give you the mass, and here's why. Keep in mind the centripetal force is mv squared over r. Friction is mu static in this case times the normal force. But if we're talking about a level curve, we've already seen from the free body diagram that the normal force is just mg. So I have mu static mg, and voila, turns out the mass doesn't make a difference. And that the acceleration that you can have going around a curve like that, your centripetal acceleration, is just the coefficient of static friction times g. This happens to be also your centripetal acceleration. So you can get it a bunch of different ways. If you know mu, you can multiply that times g. That's your centripetal acceleration. If you know the velocity of the car and the radius, you can get it that way. So this relationship will be important. You can jump all over the place with that thing, find out different things. So hopefully that helps you get these types of problems done.